Technical University hat on. Your floor, Ramona. Thank you.
Okay, thank you very much for covering these minutes. Okay, so this presentation today will be about voice services integrated into 5G networks, and mainly about IMS and over-the-top voice services. Some highlights or insights from the experimental evaluations that we have done in the recent months. First of all, let's put a bit of introduction to the entire work we are doing at TU Berlin, the chair of Next Generation Networks, led by Professor Magedans. Well, I'm coordinating the OpenSIGGNet.org initiative, where actually we are promoters of an OpenSIGG for all. We, for research at least, but not only, but regarding research, we want to achieve a collaborative research infrastructure to empower the connection of the not yet connected, connect the unconnected. This is not our idea, it's already promoted by IEEE, but we are defending this vision. So we thought if we approach technically like using open source projects and cost-effective commercial off-the-shelf hardware solution, we are able to enable rapid prototyping and deployment of test beds for mobile networks towards 6G. So we are looking to optimization of the 5G technology, because we are already trying to figure out how 6G in not even 10 years from now, but probably there will be 10 years from now, as 5G started with a bit of delay, and between each generation are approximately 10 years, let's say. And what we see as impact of benefits of this initiative, I could mention creating self-sovereign networking capabilities, facilitating customized solutions across industries, promoting inclusive technological advancement, and empowering the various stakeholders through accessible infrastructure. So we want to make these mobile network technologies more accessible, in one word. Our key achievements so far could be seen in three categories. So on one side, we have academic contributions, we publish papers, we try to foster these research activities. On the other hand, we have educational initiatives as building future talent. We organize workshops for students and try to come closer to them and see how they can get started with technology. Sipkate said it's easy to get started. It is easy, but not always, because it's not just installing the application. Sometimes it's the background information, the technology itself that the students have to get familiar with. And in case of mobile networks, this is quite complex. And another achievements that we can mention are scientific workshops that we organize in an endeavor of fostering international expert collaboration, fostering industry academic knowledge exchange, while focusing on sustainable networks. Such an event there will be next month in Budapest, focusing on connecting the unconnected with 6G networks. A bit about the roadmap. If I have to sketch it, I will sketch it like this. We started in 2023 with the core vision, and since then we worked on defining the open source-based blueprint framework. We partnership with University of Cape Town in South Africa. We had a longer collaboration with them, but it was just the right moment to embark on more collaboration. And we are actively involved now in developing the infrastructure. Our focus is on local testbed cost efficiently. This is a must. And also on testbed or replicable experiments as a service. And this we can do it with slices RI, which are kind of scientific large scale infrastructure for communication, computing, experimental studies. This was a project started several years ago by Sorbonne University, and they maintain it. We are looking to extend partners network, and we expect to have the integration work done by 2027, and in 2028 to see what was the impact of our initiative. So, yeah, at TU Berlin, we look at the end-to-end mobile network testbeds realization, including the backhauling. For backhauling, we also need cost-efficient solution over best effort networks. And we are looking at automatic deployment and orchestration, and also at multimedia services. And in the next minutes, I would like to go into more details about the multimedia services experimental evaluation that we've done last year. For example, looking at IMS and over the top, I don't know, maybe many of you already know, IMS is a standardized technology, OTT, no. But they both come with advantages and disadvantages. Okay, for telecom guys, probably there's no OTT that they really want to see. They want to have IMS, and this is a good thing. It's just that IMS is a bit more complex, and it doesn't allow for faster innovation. So we will see in the next slide. 5G standalone means that is a network, a 5G network that does not rely on 4G anymore, because it exists also 5G non-standalone, where actually the core network is a 4G core network. And having the 5G standalone will bring a lot of benefits also for voice, because then we will we'll have voice calls in with higher voice quality and lower latency. What brings new compared to 4G is the unified network for voice and data. We will have seamless connectivity, so you don't have to tear down the data session when a call is coming in. We have access to support for advanced features like network slicing and multi-access edge computing. So there will be a set of benefits having voice over new radio. This is a slide where I thought to put the architecture of voice over new radio in parallel to over-the-top voice services when you want to integrate this in a private 5G network. And we see that there are huge similarities. The 5G network, it's mainly the same, the UE, G0B, 5G-C, these boxes are the same. What is different are the radio resources that are allocated especially for the audio calls in case of IMS, Therefore, we see there an IMS PDU session. What is not present for over-the-top voice services, where the audio is sent over the internet or the default PDU session, which is the best effort, is not guaranteed bit rate. And what is also different that on the UEs, we need a SIP client app installed in order to place calls. Yeah, okay, the boxes of the voice service part are also different. For OTT, it's much simpler. It's just one Kamailio SIP server with database backend, but in case of IMS, we have 3 Kamailio servers, the PCSCF, ICSCF, and SCSCF, that have to be configured as per 3GPP specifications. And now a bit about our test beds. The simplest one that we have is running everything on a notebook that is paired with the radio unit, and this is a base station, a 5G base station. We have used the machine to install also the Open5GS and Kamailio on it, so we have everything in one place. We call it nomadic node. We use commercial off-the-shelf smartphones, so Nokia X30 in this case, and programmable SIM cards. And here we have more or less the same setup, the same computer and the radio unit, where Open5GS and Kamailio are running also on this computer. Okay, the SIP server box is missing here, but probably it's on the other slide. Yeah. A variation of the testbed, for example, we can let Open5GS running on another machine, and in this case we said, okay, in the cloud. We have servers hosted in the cloud, and we decided to have the 5G core network and the SIP server remotely. Mainly it's the same setup, just we distributed a bit the software components. And with this being said, just a bit more technical specifications, how the radio access network was realized with the open source project called SRS-RAN, and we configured it to use 40 megahertz bandwidth, and we set up the right frequency that is allowed to use for private 5G networks. Open5GS, we need to mention for those that are not familiar yet with, is using TAN interfaces to handle the network traffic to and from the UEs. So OGS TAN is the interface that provides the data services connectivity, and then there's another similar interface that is used for multimedia service traffic. And now about the experiment, we just run 10 calls of each type. And we are capturing, before starting the call, the traffic on the corresponding TAN interfaces in each case for later analysis. We went for 3 KPIs. The call setup time, that it is defined as the time between 100 ringing and invite on the PCSCF component, and another 2 indicators of the audio quality, the packet lost and the jitter on the RTP flows. These values that are displayed there are considered healthy value for not affecting the quality of the audio call. And yeah, here is just a visualization of a real voice over new radio call SIP flow that was taken and displayed with Wireshark, and the call setup time, how it was defined. And now going through the results that we got with our implementations, we come to the conclusion that the call setup time for our setup, the distributed one, so where every core network and the SIP server are in the cloud, requires almost 1 second, so 0.9 seconds. And for over the top is 10 times shorter, 0.09 seconds. One can have a rough estimation, okay, the difference in these times, it's mainly due to the entire mechanism that voice over new radio needs for reserving the radio resources before the call can be initiated. The same measurements in case of the in-a-box scenario, so everything is running on a single computer. And we see here shorter call setup times because you don't have the messages that have to go from local base station to the cloud server. So 0.35 and 0.06 seconds for voice over new radio and for over the top. So a summary of the results will be, the main outcome was that, okay, for reserving resources in the in-a-box scenario, it took 0.03 seconds comparing to the distributed setup where we had 0.08, mainly to the round-trip time to the server in the cloud. Then let's have a look at the jitter, mean jitter and max jitter distribution for, first of all, for the distributed scenario. We see that the voice stream of the voice over new radio calls experience jitter either around 20 milliseconds or far below 5 milliseconds. And in case of OTT, the jitter varies quite a lot, but still under that healthy threshold in both cases. Let's see what happened in the in-a-box scenario. Mainly, voice over new radio showed the same thing, either 20 milliseconds or close to 0. OTT, it's the same variation. Also, in this case, it was below the healthy thresholds that jitter values. But what I found it interesting is that during the testing, when we placed 10 calls, yeah, we had, you see here 40 values because actually each call had two flows, RTP flows, but anyway, it shouldn't be 40. I think in this case there were 20 calls that we placed. And after 9th or 10th call, we experienced this increase in jitter suddenly, which means that, I don't want to say means, it's a signal that actually the QoS implementation in the radio access network software or even in the 5G core network software is not stable. It must. But I don't have much information on this. It's just a guess that why this suddenly happened. And it didn't happen only once. It happened in many running of the test of these 20 calls. So. About packet loss, it was quite negligible because there was no congestion in this experiment. But we also imagine another experiment where we tried to simulate the congestion in the private 5G network. And what we've done, beside the two smartphones that were attached to the network, we attached another one where to run the iPerf3 client, while the iPerf3 server was running on the server where the 5G core was running. And we injected traffic in the network. And what we see in the upper part of this waterfall diagram from a spectrum analyzer, we see while the spectrum, how the spectrum was looking when the call, an ongoing call was happening, and then we started injected traffic with iPerf3, and yeah, the orange color shows the congestion. And now we plotted again the numbers, and we see that in case of congestion, so on the upper side there's no congestion, on the lower side is congested network, and we see a worsening in the jitter, for example. The same for over the top, but still not over the healthy threshold. So practically we haven't seen any quality decrease in the call. Quality, not objectively, just subjectively, so we could state, I hear more or less the same. And packet loss, again, we plotted a congested and uncongested network on the same plot, and we see that the orange bars are higher for congested network. And what I can say, yeah, while the measurements were a bit worse, still not much affected the quality of the call. And very strange that a small subset of voice over new radio calls experienced even higher packet loss values compared to over-the-top calls. The overall evaluation where also the call setup time is showed. We had an increase in call setup time during congested network of approximately 60%, both in voice over new radio and over the top voice call. And I think that would be okay. Also kind of a small anomaly. The packet loss for voice over new radio was a tick higher than for OTT during congestion, but the difference was quite small, so no, I don't want to hurry with conclusion. So yeah, we can conclude. After seeing the experimental measurements and visualizing them on graphics, now more from the integration point of view. So voice over new radio is definitely a bit more complex to set up that over the top voice for a private 5G network. More than this, it requires voice over new radio capable UEs, which is also not easy to find currently on the market. Calls are placed user-friendly, let's say, using the phone dialer interface. And the biggest advantage maybe is that it works seamlessly also in idle mode and with a supposed guarantee QoS. For OTT, drawbacks would be that may miss calls in idle mode. There are some workarounds, but not that easy. It's a best effort delivery, but the advantage is it's easier to integrate, works on most devices, and you just need a SIP application to be installed. And you get access to all kind of rich feature services with that SIP application. Future implication of this kind of work, so our target is to have a comprehensive understanding of IMS and OTT technologies and to try to learn from each other what was done better in one and in the other, and if we can find middle path, so adopting from the other technology what was done better and integrated, and in this way to shape the voice communication in 6G networks. What I've said here, it was shortly a few numbers, but we published in the last year several papers on the topic, and they are already available by Googling. We thank you for the financial support from the German Federal Ministry of Education and Research, which supported the Open 6G Hub project. And of course, we thank Kamailio project and also Daniel for giving us some help with understanding what it has to be done for the N5 interface towards the 5G core network. If you are interested to find more about our research work, we have a website. And tomorrow we have a workshop, in-person workshop, with live demos from our chair, a selection of work in progress or work that was already done, and some presentation from companies that are active in this 5G, 6G space. So you are welcome to join us on Wednesday. Just drop us an email. Registration is free. Thank you very much. If you have any questions.
Thank you. Short time for 1-2 question, not two. Okay, I see many. I wanted to say not to keep you from the lunch, but then we can skip the lunch and have questions. Okay, you are first here, and then it's Marcus. I saw and a few hands.
We have also an online question, our first one.
Okay. I'll take it then.
Thank you. Okay, I would like to ask, in your testing, you're using the stationary UEs. Have you tried with the mobility, mobile UEs? Because there was a research going on I've been part of for the Beijing University with the Huawei guys. They were testing the mobility for voice over NR in the mobile network. With the mobility, non-stationary UEs.
Handover, you mean?
That includes the continuity of call across the handover. So we have one base station, we are moving towards second. So and there they implemented the MPTCP, multipath TCP, and they use some technology. I don't know what was on the signaling side. On the packet side, it was SIP over TCP, TLS. So the idea was to continue the call across the multiple base stations while moving in a WAN, for example. But do we have a setup here in Germany where the 5G net, this test setup is wide enough where we can drive a WAN with a mobile?
Well, you don't need to be wide enough, because the B210 that you are using is covering only a quarter of this room. Probably it's for covering 10 meters or not more than 2 offices in our building. So it's easy to achieve this handover. We haven't tested in these experiments, but my guess it should work out of the box.
They have like 2-3 city blocks where they have this coverage. They allowed it, and they physically move across.
Yeah, it's about physically moving from the coverage area of one base station to the other. But if you have handover working in the 5G network, so I don't see any problem of your services working well on top of it. So actually, it's about the 5G infrastructure. If you have handover implemented in a 5G private network, then it's working by default. And I don't think we have nowadays a problem with the handover. But we haven't used it.
It's supported in Open 5Gs, the handover?
I haven't used it personally, but I guess so. I hope,
Okay.
I don't know.
It is? Okay. Marcos here?
Thank you for the insights. Yeah, we're typically running an OTT service for more than 2 or 3 years called Satellite. It's a German mobile number in an app, so on the user space of the phone. And I have 2 questions. Which codec do you use for the tests on the OTT side? And have you ever put the phones under load? So I would guess that the native dialer application and the OTT service will have different process priority on the phone itself. So if you do like image indexing in the background, if this will have an impact on the OTT voice quality or not?
We haven't done this stress testing. Yeah, this is a good idea for our next paper, so to say, if you want to be part of it. Why not? With this suggesting in which direction to advance the research. No, we haven't done. And about the codecs, I have to say now it's a while since I saw these Wiresharks, the PCAPs. And I think it was EVS for voice over new radio. But it's a matter of the capability of the UE. So it is chosen by default. We cannot influence this.
OTT part?
And with OTT, it was not EVS. With OTT, it was something else. But no, I don't.
Like Opos or?
Yeah, Opos. But we tested with several devices, and then you get the different. But Opos was quite a lot displayed. Yeah. Yeah, we should add also this information, what kind of codecs were used, actually, because I find it pretty important.
Okay. Here.
Yeah. I have the probably continue last one, but from the carrier side. For the OTT calls, it's anyways needs somehow to guarantee quality of service to get the proper quality. Did you did some maybe research or tried even some exchange some parameters with the carriers which guarantee somehow traffic for the voice traffic carried by over the over the top? Yeah.
No, I'm not sure I understand the question.
So I mean, so the OTT traffic becomes just usual traffic for the carrier.
Yes, yes.
Yeah, so there is no difference. But maybe you did research, or maybe some standards become in development for prioritization of this normal usual traffic, in case like if it's voice or video traffic, to be more to be better.
Yeah, I got it. I don't have exact insights here, but I quite guess there is something already in place because OTT behave unexpectedly good.
Yeah, there is on IP. We have also on Kamailio, but doesn't make big difference for the QoS of SIP packages. But I think also on RTP engine you can set there is like a bit or so with some priority on. That's only IP layer. So if the OTT, or not the OTT, the operators follows that by using the usual IP routers, should put some priority on them. My conclusion, as I'm not much into the mobile network technology, but when I saw these results, it's like, okay, so if the OTT works bad for you, probably it's the operator that delays it, which was not.
The RTP packet is inside GTP, and I think on the GTP layer there's no quality of service for each stream.
Yeah.
So, no.
But then when it's going, okay, from the core network over the internet to the other device, so like.
That depends on the carrier.
Yeah, okay. You had the last question because we get late with the lunch.
Yeah, it's just a continuity of this. Okay, sorry. It's just this continuity of this concept because we are involved on some projects, on research projects related with improved latency and improved conditions on congestion, and we always focus on voice over new radio and new concepts to provide quality and reliability to the transmission of signaling and audio. But these results were opposite. These results points to an OTT just providing better service because...
yeah, but it has, we have to limitedly understand it because we had a very small setup, just one cell, just one 5G cell, and with 2 UEs attached. So nobody disturbed us. It's not under real conditions.
That's what my main question is. If you consider that maybe the server-side implementation could compromise these results, and also the other question is why or how you could explain that voice over the new radio that it's defined to perform better, and that's what we are defending. It's working worse than this.
No, it's not working worse. They were both were under the healthy threshold, so they were behaving both quite okay. So none of the measurements went above of the healthy thresholds that were somehow defined by 3GPP in the specification. So the call setup time should be under 2.5 milliseconds. 2.5 seconds, and the RTP, jitter, and packet loss values are also defined in this specification. So in both cases, the voice over neural and over the top, we stayed within this healthy space, but in some cases, I noticed that, we had more packet loss, more packet loss for voice over new radio. But I wouldn't hurry and argue that in general voice over new radio is behaving badly. It was just our implementation. So it might be that we missed something in the implementation, or I don't know, maybe this voice over new radio is relying on the QoS mechanism of the entire 5G system, radio access network, 5G core network. So if it's not stable yet, it's not easy to figure out where it's still space for improvement. Is on the radio access network, or is on the 5G core network? Where is the problem? Why is not stable enough? But this is a problem maybe only of the open source projects that are now available, that we use. We use the SRS-RAN and Open5G, so we can speak only for this. And at that point when we did the testing, because maybe meanwhile there are new releases, and it would be good to redo the test and see if the problems, the measurements change. But it was a starting
Maybe the
point.
conclusion is that both technologies are good. One, it's maybe seamless, like using the dialer. The other one has the overhead of installing the application. But you should not worry from technological point of view that you get worse quality with one or the other. So what fits better for you would be good now to use. Matthias, not to.
So our online question, maybe it's an easy one. Why don't you use eSIM cards instead of normal SIM cards?
eSIM cards involves a third party administrating them. And we don't want to depend on third parties, but we would like to look into this also in the future.
Okay, thank you.
Okay, thank you, Ramona, because we are 15 minutes late.